So in stochastic gradient descent, what you do is you take one sample at a time, feed it to the network, calculate the loss, and then update the weights. So you're updating the weights after feeding each sample. So you're feeding one sample at a time and then updating the weights. All right? So that's what stochastic gradient descent does. So you take in one sample at each iteration. You perform the weight update for each sample at a time. So in this case, the number of iterations per epoch equals to the number of samples. Okay? Because you need to pass through all of your samples in order to complete one epoch. And in stochastic gradient descent, you're passing in one sample at a time. Okay? So each pass of this is called an iteration. So therefore, the number of iterations you have is equal to the number of samples. So if you wanted to represent it mathematically, then for each sample, xi and yi, okay, so xi is your input, yi is your expected output or your target, we're gonna update the weights. Okay, so the same rule, the new weight equals to the old weight minus the learning rate times the differentiation of the error with respect to the weights. Okay, and this error here is calculated for one sample only. So xi, yi. This is one sample. Alright, so in this case, n equals 1. Now if we visualize the example for stochastic gradient descent, then this is what we have. So this is your data set. It consists of 8 samples again. Each sample has 3 features, and that's why we have 3 input neurons. So we're taking in one sample at a time. So this is the first sample, feeding it to the network, calculating the error, and then updating the weights. Then you finish updating the weights for the first sample, you take the second sample. Same thing, feed it to the network, calculate the error, update the weights. Third sample, fourth, fifth, sixth, seventh, and eighth. Okay? So you take in one sample at a time and then update the weights. So each time you do this, then this is called an iteration. So this is the first iteration. This is the second iteration, third iteration, fourth, and so on. So in this case, you have 8 iterations. And once you finish all of these 8 iterations, then you finished one epoch. Okay, so remember, an epoch is a complete pass through all of the samples in the data sets. So in this case, we need 8 iterations to complete all of these samples. So this is what stochastic gradient descent is. You're calculating your error based on one sample and then updating the weights. And then we're going to repeat this step for all of these samples. Okay, so in the next video, we'll be talking about mini-batch gradient descent. Oh, but before we do that, there's something I forgot to show you, which is basically that stochastic gradient descent tends to be noisy. Okay? Because you're doing this for one sample at a time. So each sample might have its own weights that are needed. Okay? So since you're doing this for one sample at a time, therefore your graph would be very noisy at the end. Your loss function would be very noisy. So for example, you're going to have your loss function increase, decrease, increase, decrease, increase, decrease. So you're going to have a lot of noise in your loss function. But eventually, of course, you will reach the optimal solution. And in fact, stochastic gradient descent, especially with momentum, as we're going to see later on, sometimes outperforms all of the other optimization algorithms on some specific tasks. Alright, so there's a lot of optimization algorithms that were developed after stochastic gradient descent. So we're going to see later on RMS prop, then ADAM optimization, and we're going to see also some optimization algorithms that were proposed very, very recently, like this year. Okay? We're going to look at a lot of optimization algorithms. But after all, sometimes, this is according to research, stochastic gradient descent with momentum outperforms all of the optimization algorithms on some specific tasks. Alright? Not on every task. So this is very strong at the end. Even though it's noisy, but you will reach, somehow you will reach to the optimal solution at the end. It's just going to take some time. Okay, so that's it for SGD. In the next video, we'll be talking about mini-batch gradient descent, which basically takes the best of batch gradient descent and stochastic gradient descent.